We're very pleased to have Professor Arvind come to us from Punjabi University as well as Aizer Mohali. And we've been trying to get Arvind for a very long time now, so it's a real pleasure for him to come. A brief background about Arvind and his work. Arvind completed a master's in physics from IIT Kanpur and then a PhD in physics from the Indian Institute of Science. Has taught and worked in multiple places, including Carnegie Mellon, including Punjabi University, where he is the Vice Chancellor now, and Aizer Mohali, where he was one of the founding members, as well as the Dean of Research and the Dean of Sciences. But very importantly for us today, he's one of India's best-known quantum physicists, and I think quantum physics is an area that we have increasing interest in right now. In fact, he runs a large group at Aizer Mohali doing quantum cryptography and quantum computing. So they're all things that we, I think, find very fascinating. And speaking for myself, I think we know very little about these things, but we would like to understand them. But Arvind also, which is the other reason we've called him for the colloquium, has a long-standing interest in science pedagogy and in communicating science very simply and very in a very interesting manner, not just focused on the science itself, but relating it to many other aspects of everyday life, the science, the social sciences, the humanities, altogether, and taking that out to colleges and schools. So for instance, he runs a large program where they do this in Gurmukhi across Punjab with government schools. And so all of this put together, I think it's a lovely opportunity for us to come and have this very nice talk from him. So Arvind, over to you.
First of all, I'm thankful to the organizers for inviting me for today's talk, and specifically to Professor Harni Nagendra, who kind of took initiative of writing to me, and then I could not come last time, then it was kind of the schedule was modified and so on. What I'm told is that I am talking to a very broad-based audience, undergraduate students who are from sciences and also from non-sciences, but definitely not the physics students alone. And I quite like talking to broader audiences because I have a vested interest. I'm a very selfish person because some of the questions which people from other disciplines ask are those things which make you think and wonder about what you are talking about. And that kind of a dialogue and exchange is something that I'm looking for. And when you talk within the discipline, that many times does not happen. Now, 2 or 3 things I want to say in the beginning to tell you the format of today's interaction. The first one is that I don't have to reach anywhere in these slides. So we could stick with the first slide itself and talk for a while. And if you have enough questions, I don't even need to go to the second slide. So what I mean to say is that there is no specific material that I want to cover in this talk. Idea is to give you a glimpse and a certain historical background and some idea of what quantum world is all about, how quantum world is different from the world we live in, and what are the new exciting things which are happening in the field of quantum physics or quantum technologies or quantum information and so on. Quite a bit part of the talk will be a historical perspective because I know people are coming from different disciplines. But you can stop and ask questions and we could begin the interaction whenever you want. And that will also, in some sense, help me take my path through this talk. All right. So I have divided the quantum revolutions into 3 revolutions. So quantum mechanics is a purely 20th century thought. There were no quantum ideas in the 19th century. But it's important to take a look at where physics was in the 19th century. Physics was quite a well-developed discipline in the 19th century. And so much so that, you look at it, I mean, Newton was 17th century. Before Newton, there was a Galileo who did so much work. So by 19th century, we had thermodynamics, we had mechanics. We also had electricity, magnetism, and Maxwell equations, a beautiful field theory. So physicists were thinking that they know almost everything about the world. And to that effect, Lord Kelvin gave a talk in which he said, well, we are almost there to know all the things. And these few things are left. And in the coming few years, we will close this chapter called Knowing About the World or Knowledge or Physics or whatever that is. However, the history of physics kind of unfolded in a completely different way. Very quickly, people realized that you see things in the world which cannot be explained using 19th century physics. Now, I will give you one example. There are many examples, but let me give you one example in some detail which you will be able to connect with. You all know that if I heat material, what happens? Heat is basically motional kinetic energy of the molecules. So molecules begin to move fast, more heat, faster, and they move in all kinds of random ways. Why we say that? Because hot object doesn't leave this room, it remains in this room. So they don't pick up kinetic energy in a given direction. It's all kind of random kinetic energy which we call heat. So that's the reason when you put your finger into a cup of boiling water, those fast molecules come and hit the molecules in your skin, break it down, and you get wounded. So it's actually breaking off your skin long molecules, polymers, by the hot, fast molecules of the gas. So heat is motion, random motion, and that we perceive as heat. Now, you see, when objects are heated, typically what happens when you heat a heater coil, it emits some radiation, some light. Sun is very hot, so much light comes from sun. So why is there emission of radiation or light when we heat material? Well, from electricity, magnetism, or electrodynamics, we learn that all radiation is electromagnetic. So roughly speaking, if I take a charge and shake it like this, so electric field around this charge will oscillate, and that will move out like a wave. And that is electromagnetic radiation. Light, X-ray, heat, IR, all is just that. Shaking charges, moving charges produce radiation. All right. This is also 19th century physics. Heat is energy. That is also 19th century physics. Now the question is, random motion of charges produce what kind of heat? Well, it's random motion, random oscillation, so random heat. So random heat means what? Random light means what? All colors, right? I mean, no color can be preferred. So this is very simple logic based on 19th century physics, that hot objects should emit radiation which has all frequencies, all kinds of random things in it. However, those of you who have gone to chemistry lab, we do something called a flame test, which means that when you heat a material, what do you do in a flame test? You take a little bit of that material, heat it at a very high temperature inside the flame, and you get some very specific colors which are characteristics of that material. Like the sodium light is yellow, and you must have seen this crimson neon light, which is very specific crimson color. So when materials are heated, they don't produce random light. They produce light which is very specific, characteristic light of that particular atom. Why is this happening? No way 19th century physics can explain this, that heat is random, you are heating something, but what comes out as radiation or light from those elements are very specific to those elements and very precisely defined frequency and color. So there's no way you can explain. So this is one very important set of things which were measured in the beginning of 20th century, which have no explanation in the 19th century physics. Well, today if you look at this room, most of the things can't be explained using 19th century physics. Why is wood non-conducting? Why is stone hard? Why is iron conducting? Why is mercury a liquid? It's a metal. Other elements around mercury are solid. So none of these things can be explained using 19th century physics. So more you see that actually this arrogance of 19th century physics was completely ill-placed. Similarly, there is another phenomenon which you might have heard more than the radiation part that I told you, which is called photoelectric effect. Now, all of you, I mean, even the social science students would have seen solar panels. So all of us are using solar panels. So you have a solar panel in which you expose certain material to radiation, solar radiation. And what happens? The photons or the light comes, hits the electrons, knocks them out of the material, and then we collect them, and then we start a current and we get energy. So what is seen is that if you have low frequency light, even if you put a lot of low frequency light on a solar panel, no current will come out. Then you need to put a certain color of light. Only then the photon will come out. Why so? Why can't 20 weak photons knock off one electron? No way 19th century physics can explain this. That why can't we just add on small efforts and knock out one electron from the atom? Why do you need a specific photon or a quantum of energy to do this? And so on and so forth. So lots of experiments were done in the beginning of 20th century which had no explanation in the 19th century physics. So then this framework which we call today as the quantum framework was invented. And this framework was invented in the first 22 years of 20th century, which explained all these and gave us a very different way of looking at the world around us, which today we call quantum framework. So this I call is the first quantum revolution. After that, once we had this framework, which was initially designed to explain phenomena around us and specifically atomic phenomena, people started applying this to other things. And we saw a huge development of applying quantum framework to the world around us, all the way from to objects which are much, much smaller than atoms, like the nucleus inside atoms, or within nucleus, there are quarks and so on. All those are also their properties, and all what they do is explained using the quantum framework. And on the larger side, you must have heard about supernova explosion and Chandrasekhar limit of stars. That stars, if they are larger than a particular size, they blow up before their death. And that calculation of Chandrasekhar limit is a purely quantum calculation. So quantum framework, which was invented for atoms, is kind of applicable all the way from things which are billion times smaller than atom to something which is billion times larger than atom, which is like a neutron star. So this has been one of the most successful framework to understand the world around us. And therefore, physicists were busy applying this particular framework to whatever they found, whether it is superconductor or materials or whatever, and stars and atoms and molecules and solids and so on and so forth. And lot happened in this period in terms of understanding the world. And lot of that you also see having translated into technologies, which we will see in a minute. However, there's one more revolution, by the way, which is a purely 20th century phenomena. Can you tell me? Something which was not there in 19th century. Relativity was well in the very much there even in Galileo's time. You talk about Galilean relativity. It only the principle of relativity which changed a little with Einstein. So this idea that you should be able to look at the world from different frames of reference is old, at least as old as Galileo. So relativity was not a thought. Idea of relativity is not 20th century. Something outside physics, something which is no way people could conceive in the 19th century. Genetics, okay. Genetics also the motives for life people have been talking about, but I heard the answer somebody was talking about. Idea that machines could compute. There is no such thought. Machines could do work, machines could be power looms, engines, all that. But computing machines is a 20th century idea, and it also developed very nicely in the beginning of 20th century in terms of a theoretical framework and practical computers. Again, I have deliberately put these dates in the middle of 20th century. And quantum physics played certain role in providing motifs to build computers. That's all. So it's a very passive role that you have transistors and all that and so on, out of which you build ICs and then you compute. But the way you think about computing has nothing to do with any quantum framework. You have a certain logic, and that logic gates are used for computing. So another revolution was happening parallelly with the quantum revolution, which we call the computing revolution. Now, what happens in the end of 20th century? I have put 1984 for a reason that certain work got done, but primarily I would say last 10 years of 20th century, that people started asking a very different kind of question, that the quantum framework that we have built, and you will see how quantum framework is very different from our regular classical framework. It is a very different way of looking at the world. The logic of the world is different. That I have not yet told you. But the question people started asking is that, can that be used to do computing in a different way, or to do communication in a different way? So that I have called as the third quantum revolution, where quantum ideas are being used now to reinvent the idea of computing and communication, and that is leading to quantum technologies. So that is the era we are living in. That's more or less a 21st century game. And if time permits, I will talk about that also. So at this stage, if you have a question, you could ask me, because I've tried to tell you the backdrop in which the quantum framework developed. I deliberately am calling it a quantum framework than to say quantum mechanics or quantum theory, because it's actually a broad framework of thought. Another unique thing about the quantum framework is that it is not one person's effort. So earlier you say, Newton's laws, Maxwell's equations, Einstein's relativity. who's quantum mechanics? There are people, very many different people, from Dirac to Schrodinger to Heisenberg to Bohr, people who have contributed to development of the quantum framework. So it's not a one person's, and that maybe also reflects in the way it works. So let us go over some of these things that in the classical word, we think of the word as continuum, continuous, and the quantum word is discrete. So if you have a packet of energy which we call photon, then you can't really take little bit energy from it or add little bit energy into it. You have an electron charge. Now electron charge is a fundamental unit of charge. You cannot go to the electron and borrow little bit of a charge or add little bit of charge into it. Similarly, in all different ways, the word quantum itself means a packet. So the quantum word is kind of discrete and not continuous. But the question is it counterintuitive? Not really. A biological word is also discrete. I mean, there are whatever 200 people here. I can't say that there are 200.2 people here. So seeds are discrete, cells are discrete. So discreteness is not something that we don't know of. So quantum word is discrete. We accept it. We work with it. It helps us calculate things. But it is not something that we are not aware of or something that we don't know of. The second major departure is that superposition of classical possibilities can exist, and this is something very different. So what does it mean? It means that if I can conceive of a situation A and a situation B logically, then I should be able to imagine them together. This is difficult. If I am giving a lecture to you here today, I cannot be sitting in my office and doing a calculation at the same time. But in the quantum world, that is not forbidden. And every one of you have done high school chemistry. So in high school chemistry, they happily teach you that electron is in a s orbital. I think all of you must have heard s orbital, p orbital. So, but inside that orbital, which is a region of space, where is the electron? It can be in any of those locations. Therefore, you should also be able to conceive of the electron in all those locations at the same time. Now, this is, as you will see as my discussion unfolds and you start thinking about it, this has logically very different kind of consequences, because things which are mutually exclusive, I mean, you can produce to say that you did not commit a murder, all you need to say is that on that day you were in a different city, the matter ends in the court of law. But that is not how the quantum world is. The associating location, or in a very broad sense, one possibility, and then say if one possibility is there, others cannot be there, that mutually exclusive things don't remain mutually exclusive in the quantum world. By the way, this list is in no way complete. I'm just giving you a glimpse. And third major departure is the way you use probability. Now, all of you, whatever may be your discipline, must have encountered probability. Now, what is probability? What does it represent? So if you ask me, in the regular way of thinking about probability in the classical sense, it represents our lack of knowledge. So when you don't know something, you assign probability. I think you will agree. So somebody goes to my home today and says, where is Arvind? They will say he's in Bangalore. Probably he is with Venkatachalam Suri. Probably he is go to IISc, that is his alma mater, or maybe some other institution has invited him and probably he is giving a lecture. So you assign probabilities when you don't have the precise knowledge. However, you never imagine that that knowledge doesn't exist, because you know I'm a person, I'm a professor, I will be in one place. Out of those 3-4 possibilities, I am doing only one thing. And if somebody calls somebody in this room, everyone in this room has a precise answer what I'm doing now. So this information, what I'm doing, exists. For a person who doesn't have that knowledge, you assign probability. Let me give you a little bit more scientific example of this. Let's imagine that I have a molecule with me and it emits UV. So it absorbs heat, emits UV. Of course, it is not visible to any one of us. And you know, these days you have ways of picking up a molecule. So I had a scope through which UV could be seen. I saw the molecule, I picked it up. I saw it is in my hand. Now, one of you has a probe, so one of you can see it. So we use that individual to find out where is the molecule. So I ask him, do you see the molecule in my hand? The person confirms and you all agree. Now what happens is that individual goes to sleep and I release the molecule. Now I ask you, where is the molecule? You don't know, I also don't know. Then some of you are physics students, you know thermodynamics, you will say, oh, now it has equal a priori probability of being everywhere in this room. It has disappeared in this room, cannot go outside this room because room is closed. That molecule has been colliding with gas molecules. So it has equal probability of being everywhere in this room. But when you say this, all of you know that one molecule, it is in one place. So if we wake up that individual, he brings back his scope which can see UV. He says, what are you talking about these probabilities? Oh, molecule is there. And we know that that reality exists. And therefore, we are happily using probability very comfortably. Now, in the quantum world, that is not the case. You have to accept probability as a fundamental entity. All right. Now, what does that mean? So, let us imagine that I have a bunch of radioactive nuclei. So, let's assume each of these monitors is a radioactive nucleus. 1, 2, 3, 4. There are 4 of them in front of you. And there is a half-life of, say, 5 minutes. Now, quantum mechanical calculation will tell me that after 5 minutes, 2 will decay. Because they are radioactive, they decay into something else. 2 will remain. That's a precise calculation. But the question is, will those 2 decay? Or will these 2 decay? Or will the middle 2 decay? Or will the end 2 decay? Now, the quantum framework says, no, that is not something that you can calculate. There is a probability for decay, and as per that probability, they decay. Of course, you can say, oh, this is like that. I don't know, the quantum scientist doesn't know. But of course, in principle, somebody should be able to figure out which 2 will decay. But then the quantum machine will say that, no, it is not knowable. There is no such thing of precisely which one will decay. This probability is fundamental. And by the way, this is the aspect of quantum framework which Einstein was very unhappy with when he said that God cannot be playing dice with the universe. He was not happy with the fundamentally probabilistic model of the universe. We'll come to that. I'm going to talk about that work. So point is that one should be looking for a more deeper framework which does not have these probabilities. And today we know that such a framework may not even exist. And you may have to live with the probability as a fundamental way of nature expressing itself. So this again has philosophical implications and so on, which we can talk about. Then the next one is also very interesting feature that in the classical world, we gather information happily and keep learning. So we can be passive learners. Simplest example is you go to a library, you issue a book. You read it, you learn something, you put it back. Then I go ahead, I issue that book, I read it. It is the same big book which you read. But in the quantum world, if it was a quantum book, when I go and read the book, it is not the same book. The fact that somebody has read it changes the book. And this is a fundamental principle of quantum physics. So let me give you a more simpler version of it. So you ask, you want to find out, you want to learn about an electron. So you ask the electron, where are you? So he raises his hand, I am here. Then you say, okay, what is your energy? So electron reports the energy in the next experiment. Then you ask the electron, where are you? So the electron reports from somewhere else because the process of asking second question changes the previous answers that the electron has given. So I ask the student, what is your name? What is your class? What is your age? What are you doing? And then when I go back and ask the class can change. So more questions you ask, it is not necessary that you will get more information because every process of gathering information from a quantum system changes the quantum system. And second time, when you ask another question, the answers need not be consistent. So I know economics is very much here. I call it law of diminishing quantum returns. By asking more and more questions, you don't always learn more. This is also a principle in education, by the way, that if you give too many exams, then the students don't learn. So, this is where the analogies are important. The quantum world is like that. Though we feel that with the physical world, you are making measurements, you are doing experiments, so you should be learning more and more. But, and at a more philosophical level, the question is subject-object interaction. There is no, every subject and object has to interact. through which only you can learn something, and both you learn, you gain information, but the object gets affected in the process. So there is no way you can circumvent this. This is also is a way of saying the uncertainty principle and all that which you might have encountered, but this is a fundamental principle of quantum framework. Then the last one that I have put here in the list is that typically in a model of the world, which science is all about, you begin imagining the entities and giving them some mathematical structure. Like you say, particle. Particle means it is somewhere. So you put up dot. So dot is a representation of a particle. Then you say particle is moving, you put a momentum vector. Now that momentum vector in some sense gives you a picture of motion in that direction. So the space in which you model phenomena mathematically is very much like the space in which the phenomena itself exists. This also you have to leave in the quantum framework. In the quantum framework, the model that you build in which you do calculation is a complex linear vector space of some dimension. Is not our three-dimensional space. So when you imagine a particle, you imagine a point in that space. You don't imagine a particle in the space in which the particle is actually moving. So you build your calculations there, get the answers, and then bring them back to a regular three-dimensional laboratory and compare the answers. So I always say it's in some sense a meta framework. You have to work at a one more level of abstraction compared to normal modeling, in which you directly put in entities and then put mathematical relations and start modeling them and moving with them and so on. Anyway, that is also fine because that doesn't break any specific intuition. It just tells you that if you develop intuition in the model space, that may not be the intuition of the actual phenomena that you are working with. That's the only aspect of that. So the three features of quantum mechanics or quantum framework, which I have explained above, let me put it again, and I have added one more. First one is superposition, which is very bizarre that you have to imagine now situations together which appeared mutually exclusive in the regular classical framework. Second one is measurement, that measurements are not passive. When you make a measurement, you end up affecting the system. And the third one is entanglement, which tells you that correlations within quantum systems can be of a very different nature. I'm going to spend some time explaining this before we get into the technical details of the talk. See, the correlation means you all understand what is correlation. So correlation means that if two things are correlated, if I study one, I get to know something about the other because they are correlated. Perfect correlation means that if two things are perfectly correlated, knowing this gives me everything about this. Now, correlations many times require connection or interaction. But correlations can happen without that also, in the following sense that if they are identical twins and you measure their DNA sequence in one lab, somebody else immediately will say that the identical twin will have the same. You don't have to go and see the DNA sequence of the identical twin because identical twins. They don't need to be together at that time. Since they are identical twins, they share the same DNA. So it's a correlation. Their DNA is perfectly correlated even though they are no longer in touch or talking to each other. So there's a perfect correlation which does not even require any interaction to happen. All right. Now these identical twins go to the same class, typically wear similar clothes. Their habits are also similar. They get same homework. So if you are living in the same city in which these twins are living, you go to a cinema hall, you find one. Very likely the other one is sitting on the next chair because they see their movies also together. There is no surprise that their motion, their activities are highly correlated. Once in a while it may happen. They fall sick together normally. So no surprise. It's a correlation because they are identical twins. They are living in the same family. They're going to the same school. They're doing everything and so on. This is the classical, regular kind of perfect, strong correlation. Now what happens is that one of the twins is transported to another city, joins a different school, and time is passing. There is no phone connection between the two. They don't know. There is no communication. You have cut all channels of communication. But they are identical twins. Now a new film is released in the cinema halls. And you see one twin watching that film in a given PVR theater in his or her city. What is likely that whichever city the other twin is living would actually be watching the same show at same time in the same company cinema hall. There's no reason. It may happen that they will watch the same film, but they will be, their timing of watching that first show will be correlated 100%. There is no reason. Their interest may be similar, all that may be true. But in the quantum world, this can happen. Dynamical decisions taken in future, which are apparently randomly taken, spontaneously taken by one party, can be perfectly correlated with similar random decisions taken by the other party without any channel of communication open between the two. In such situations, we call this these entities are entangled. So this is another feature of the quantum framework called quantum entanglement, in which you could, of course, they have to share a past. So past normally is shared, and that reflects in static correlations in future, like the DNA. My DNA is my DNA, it is not going to change. But you see, if I get a cosmetic surgery done, there is no reason that the identical twin will also be undergoing a cosmetic surgery of the same variety on the same organ. So this is what can happen in a quantum mechanically entangled situation. And this leads to all kinds of interesting aspects, not just for quantum computing and quantum communication, but to think about the quantum world itself. These are the things I was going to tell you, which are all there in my first slide. And then I'm going to tell you more things, and you can raise your hands, ask a question, stop me wherever you want. Yeah, so what you call a quantum state of the world, for measurements or outcomes of measurements, it will not give you precise answers. So in the classical world, when you fully know the state, you know everything. In the quantum world, you fully know the state, which is the quantum mechanically knowable, may still have probabilities in it. So the nature itself might be at a fundamental level probabilistic. Yes, it's a classical. I mean, if you really ran a supercomputer on all the molecules and all that and so on, there was no fundamental probability involved. It's a question of complexity. Let me give you a different example. I mean, can all the molecules in this room kind of conspire and go to that corner and I die of lack of oxygen? It's possible. Right? But it doesn't happen because probability for that event is whatever 10 to the power minus 23 and so on. So, but it is not that it is not possible. So, actually sorry, maybe I gave you a slightly different example. What I mean to say is that COVID-19, if you look at the way it was propagating and all that, is a deterministic dynamics. It's very complex. So complexity leading to indeterminism is a practical problem. That's what I said, that when you cannot keep track of all the variables. Like if I release a molecule here, can I work out its trajectory in this room? In principle, yes, but practically no, because there are 10 to the power 23 molecules involved with which it is interacting. So the system is just too complex to keep track of it. So we introduce probabilities. But that is the probability to express our lack of knowledge or our inability to compute. Fundamentally, one particle has one trajectory. Yeah, so I'm not saying it easy to think, but one has to agree that you do not have a layer of non-probability below the layer of probability in quantum mechanics. That will come through in the coming slides. So the first objections to the quantum framework came from Einstein. So he wrote a paper which is called the EPR paper, Einstein, Podolsky and Rosen paper, where his main point was that quantum framework is probabilistic, but there must be a deeper framework than quantum framework, which when averaged over will give me quantum physics. So he was alluding to incompleteness, not incorrectness, but incompleteness of quantum mechanics. And his whole idea was that we should be able to do better than quantum mechanics. So Einstein being Einstein, this paper is now the fundamental paper in the field of foundations of quantum mechanics, because he challenges the completeness of quantum mechanics. Argumentation in this paper I can come to if there's a question, but it's more important that he wrote this paper. And his idea, following his ideas, many people started building up frameworks which were one step lower than quantum mechanics, in which you know which things are going to decay in principle, and then you average over those and you get quantum probabilities. So this was a project that he thought we should do. So that's why he said that God does not play dice with the universe. The dice is coming because we don't know enough, and we should do better than quantum mechanics. This is 1935. So you can imagine now that in 1935, quantum mechanics was a well-developed framework. Most people were busy applying it to various phenomena, but some people were busy trying to analyze the framework itself, and this is one of those efforts which he put together. What happened in the following years was that people who tried building these theories did not succeed much. So, of course, it takes time to build things, and people were trying to do better and better. Then in 1964 came the next landmark work by John Bell, and it's very important in these years, so that's why I brought this out. So Bell kind of turned the question around. So instead of trying to build a model, I think his orientation was more mathematical. He was more mathematically minded person. He changed the question completely because in the 30 years or so after Einstein, people were not able to make much headway with developing the framework deeper than quantum mechanics. So he said, all right, let's assume that such a framework exists, which is better than quantum mechanics, which can give you next layer, which is not probabilistic. Okay, let's assume that exists. What are the consequences of such a framework? And to the surprise of everyone, Bell proved a theorem. In physics, we don't prove theorems because all physics is tentative, but this is a mathematical question. So he proved a theorem that if such a framework exists, it will contradict quantum mechanics. So that can be proved. The two frameworks, you assume something, you prove something. So Bell's 1964 work, which is now called Bell's theorem, is basically this. He says, all right, let's take Einstein seriously. Let's assume that what he wants future physicists to do has been done. Okay, such a framework has been given. Let's look at its consequences. And one of the consequences is that it will contradict quantum mechanics. It cannot be consistent with quantum mechanics. Which means quantum mechanics is not just incomplete, it is wrong. And that is important. See, that is where it becomes a science that now you can go to the laboratory and you can find out whether quantum mechanics is right or quantum mechanics is wrong. And the Nobel Prize in Physics, which was given last year, 2022, was given for those guys who took Bell's ideas to lab and did these experiments. So let me tell you a little bit about this. So John Clauser did his experiments in the basement. He was not funded to do these experiments, and he wrote a paper in 1972, which was the preliminary set of experiments which showed that quantum mechanics is right and deeper theories based on Einsteinian logic may be actually wrong. But these were very preliminary experiments. People didn't really, people thought one should do more experiments. Of course, he paid the price. Physicists thought this was all useless work. They kicked him out. He left academia and didn't get a job, moved to industry, and came back face to face with physicists only after he got the Nobel Prize last year. Anyway, that's a story how many people in your field may interpret about what you are doing. Then Alan Aspe did better experiments than Clauser, and he published these experiments in early 80s, and his experiments showed that quantum mechanics is right, and if you try to build a deeper theory without probabilities, not having the counterintuitive aspects, that nature does not follow those constraints of such a theory. The story with Aspe is even more interesting. Before doing his experiments, he went and met Bell. And Bell told him that, do you have a permanent job or are you looking for a job, young man? So Aspe had a job. He said, okay, if you have a job, then you do the experiment, because for doing these experiments, people may kick you out or not give you a job. So he could do these experiments because he had a job. Then, of course, by that time, many more people started taking interest in these experiments. And then came Zellinger, who did these experiments in 90s. And he showed in a very, very different kind of settings, all kinds of sophisticated settings, that quantum mechanics is correct, quantum framework is correct, and the theories which we might think of building based on Einsteinian logic are actually not possible. They contradict nature. They not only contradict quantum framework. So together, these three were given Nobel Prize in 1922. Last year, so 2022. But then what are we coming towards? So in the process of doing these experiments, lot of things were developed in experimental physics which allow you to see those counterintuitive nature aspects of quantum mechanics, which have superposition, which have entanglement, which have these consequences of these measurements. So we have now learned how to see those very nuanced aspects of quantum world, quantum nature. All right, so immediately what those aspects are telling us, that you could do computing in a different way. Now I'm changing gear at this stage to tell you about the third revolution. So to set the stage more properly, the first revolution was development of quantum framework. Then one whole thing was applying quantum framework to different phenomena. Along with that, people were trying to poke the quantum framework and try to see whether it is right or wrong. But by the end of 20th century, we are now beginning to think that the counterintuitive and a different logical structure of quantum mechanics is not just in our mind, it is also there in the world around us. So now, can we use it for something as interesting as computing or communication and so on? Now, I will not give a full talk on this. I will just expose this to you a little bit, and then maybe at that stage, I will stop and take questions from you. All right. So, two very important problems which find a solution based on quantum ideas is Shor's algorithm of factorization in polynomial time. I think it is not difficult to understand that factorization, which is inverse of multiplication, is not easy. Multiplication is quite easy. Maybe it's all right to spend little time to understand how do we see difficult versus easy problems on a computer. So what people typically do is, if you change the size of the problem, you ask the question, now how the time taken to solve the same problem of a bigger size changes with the size of the problem. So let's take, if I want to find out a number is even or odd, does it depend on the size of the number? No, right? Which means the problem is so easy that you give me a small number or a big number, I can immediately tell you without much effort. So the time taken to solve this problem is independent of the size of the problem. How about addition? That takes little more time if the numbers are large, but is it proportional to the numbers? No, it actually is proportional to the number of digits in the number, which is log of that number. So that's again not difficult. So that way you classify. So multiplication is also not that difficult, but inverse of multiplication, which is factorization, is extremely difficult. In technical terms, we say it's exponentially hard, which means if you give me a very large number, to factorize, I'm going to take, very quickly I can come up with a number that the time taken to solve it on a computer will take semi-infinite time. So such problems are called not doable in computer science. In a very loose ways, I am telling you this. So factorization is such a problem, and Shor proved in 1996 that if you have a quantum computer built on the principle of superposition, entanglement and so on, you can do factorization in polynomial time, which means the factorization becomes a solvable problem from the domain of non-solvable problems. Then of course, another interesting algorithm due to Lovegrover, where you get a square root advantage in searching databases which are unstructured. If there are questions, we can get more into it. But point of this talk is that these counterintuitive aspects of quantum framework are not only there in nature, they can be employed to build computing devices. The last part of my talk is that is related to the question which was being asked and which I spent some time on, that there is no way of passive gathering of information. So in the classical world, if two people are talking on the phone, I can always tap the signal and listen to their conversation. Fundamentally, there is no restriction. So if they have put a pipe, I can look through the pipe. If they have put a code, I can put a decoder. If I don't know their code, I can employ a computer scientist to decode their code. So all channels in principle are open to eavesdropping, and you can listen to the signal. So this is the whole area of cryptography. How do I do secure communication? In the quantum world, you can turn around this problem and you can say that at a fundamental level, when Eve is trying to eavesdrop, Eve is actually learning something from your signal. And by that measurement thing which I told you, therefore Eve will leave some impression on your system. So you can detect that somebody is coming and actually try to learn about your system. So that's the fundamental thing. So if Eve learns X amount, Eve will disturb Y amount. So therefore, if you keep track of your system very carefully, you can find out that somebody has been trying to come and tamper with your system. Based on this, you can build fundamentally secure quantum systems. This is the quantum cryptography scheme based on entangled states. So use quantum entanglement, the kind of correlations I was telling you about, and you take these correlated quantum entangled particles, distribute them into two locations, and that can be used to do unconditionally secure quantum communication. So maybe this is a good point to wind up. So these aspects of quantum framework are now leading to quantum technologies, quantum communication technologies, which are called quantum key distribution devices, which have gotten quite advanced now. You can even get commercial devices all over the world. People are building these. The second ones are quantum computing devices, quantum computers, which when built can in principle solve problems which the regular computers cannot solve. And here also a lot of progress is being made all over the world to build quantum computers. And the third one is quantum sensors. So one quantum sensor which is very famous is the gravity wave detector. So you know people are wanting to detect gravity waves. So you do that by using a Michelson interferometer on Earth, but then you have to do a quantum analysis of that interferometer to improve its sensitivity. So you send in certain very delicate quantum states. So quantum sensing is a big field now. So these are the quantum technologies which hopefully will become kind of possible within this century, or even by maybe next 20-25 years. And then it's very exciting that to build these quantum devices, what kind of quantum systems are being used. So people use superconductors, people use photons, states of light, trapped ions, people also wanting to use semiconductors, the spins inside nuclei in a liquid state NMR or a solid state NMR system. So there are many candidates, and we really don't know which kind of quantum systems which finally lead to quantum devices or quantum technologies. And well, I must end by telling you that in India, we have had a QUEST program, Quantum Enabled Science and Technology Program. And now we have launched a mission called the National Quantum Mission. Original name was National Mission on Quantum Technologies and Applications. Now it has been changed to National Quantum Mission. And under this funding and all that, Government of India is making available to develop quantum technologies in-house. The various labs which are doing this kind of work are located all over the country. I've just given you a map. So everywhere, Bangalore has many centers, Institute of Science, Raman Research Institute. There are two places where such research is going on. My own interest is more in the counterintuitive aspects of quantum mechanics than seeing these technologies work in future. That's also very interesting for many people. To summarize, I told you the story of how quantum framework came up, how it is very different from the way we think about the word in the classical sense, and how, on the one hand, it explains a large variety of phenomena in the physical world. And in 21st century, it is leading to new technologies, which we call quantum technologies, where quantum physics or quantum ideas are not used in terms of using quantum properties of matter. The quantum ideas are used in the very conception of the framework in which we are thinking of our technology, whether it is communication or it is computing. Thank you.